This is Chapter 4, Section 1, Graphing Polynomial Functions. We're moving away from the quadratics, like we covered in Chapters 2 and 3, and moving into things that are bigger. We're moving into cubics and something with x to the fourth or x to the fifth. Okay? And what we're all discussing here are what's called polynomials. So polynomial is a monomial or a sum of monomials. A monomial would be something like 3x, or let's come up with something like 9a squared, or negative 31z y cubed. All of those are examples of monomials. Now, a polynomial, then, all we need to do is add them together, or since it's a minus 31 here, we could just continue that as a negative, or make that minus 31zy cubed. Okay, that would be an example of a polynomial. Now, it's a very complicated polynomial, but a polynomial nonetheless. Next vocab term is a polynomial function. That's what we're going to be working with mainly in section 4.1, or chapter 4 completely. Polynomial functions. Function with the following characteristics, okay? Your exponents have to be whole numbers, meaning there won't be any negatives, or there can't be any negative exponents. There can't be any fractional exponents. And then the coefficients are real numbers. So we're not going to be working with imaginary numbers right away. We will come back to them when we start solving polynomial equations. But for now, the coefficients aren't going to have any imaginary parts to it. It's all going to be numbers like 3, 9, negative 31. You're never going to see 3ix, or 9ia squared, or 31izy cubed. Okay, all of these coefficients are going to be real numbers. Okay, next vocabulary term, leading coefficient. The leading coefficient is the coefficient on the variable with the largest exponent. Now, with this one, it's a little tough to see because we've got different variables. If all the variables were the same, then it would be pretty easy. So let me give you an example. So if we had something like, I'm just going to make this up here, 4x cubed minus 15x squared plus 11x minus 17, the leading coefficient is the coefficient on the variable with the largest exponent. Well, the variable with the largest exponent is right here, x to the third, so the leading coefficient for this polynomial is 4. Okay? Next vocabulary term is the degree. The degree is simply the biggest exponent. So in this case, this would be a degree 3 polynomial because the biggest exponent is 3. The next vocabulary term is constant. Whoops, go back to the pen. Constant. A constant is a term with no variable. So in this case, that would be the 17. So I'm actually going to underline these in different colors. So the constant I'll do in orange. That's this. The degree we'll do in red. The degree is the biggest exponent. And then the leading coefficient we'll do in green. The leading coefficient is this one, okay? So the leading coefficient, the number on the variable with the biggest exponent, the degree is the biggest exponent, and then the constant is the term with no variable at all. Okay, the last vocabulary term here for a while is standard form. Standard form means that the terms of the polynomial function are written in descending order of exponents from left to right. So the biggest exponent comes first, then the next biggest, then the next one, all the way down to the term without the variable at all. Because really, this one does have a variable. This would be like x to the 0, and anything to the 0 power is simply 1. So they don't. If it's x to the 0 power, they don't write it. Okay, so standard form terms are written from left to right in order of descending exponents. Now, I'm going to draw a little bit of a table here. Okay, it's going to have 3 columns. The first column is going to be degree. Okay, the second column is type, and then the third column is example. Okay, so I'm going to show you different types or different kinds of polynomial functions. The lowest degree you could have is degree 0. Okay, if it's degree 0, that is what's called a constant function. Okay, it's a constant function. An example of that would be something like f of x equals some number. Okay, just a number, 2. So the graph of this would be a horizontal line straight across at the y value of 2. Okay, the next degree up would be obviously 1. Something that is degree 1 is a linear function, and this is all algebra 1. F of x is equal to something like negative 3x plus 1. Okay, it's a linear function. We have a slope, we have a y-intercept, we go up at the same rate or down at the same rate. That's what makes it a linear function. Next degree up, degree 2, this is what we covered in chapters 2 and 3. This is a quadratic. And I'm running out of room. Quadratic. Okay, so an example of this would be f of x equals 5x squared minus 16. Okay, you don't need every term going down in every example. So even if it was just 5x squared, that would be a quadratic function. If you wanted just x squared minus 16, that's also a quadratic function. You don't always need a number out here. You don't need something on the end. You don't need every variable in the middle. Okay, as long as the biggest exponent is 2, that makes it a quadratic function. Okay, next one up is 3, and anything to the third power is cubed. So a degree 3 polynomial, let's call it a cubic function. Okay, so that would be f of x is equal to something like negative 6x cubed plus 2x squared minus 7. And these examples, I'm just making these up off the top of my head. There's no rhyme or reason to how I'm coming up with these. These are just examples of these types of functions. Okay, last one I'm going to show you, pick a different color, we'll go with orange here, degree 4. Okay, degree 4 is called a quartic function. Quartic function, so f of x is equal to, if it's degree 4, the biggest exponent is going to be 4, so we're going to have something like x to the 4th minus 14x cubed plus 11x, and we'll leave it there. Okay, though that would be an example of a quartic function. You don't always need a constant term. Don't always need every exponent going down. And obviously, I missed x to the second power, so 4, 3, and then down to 1. Okay, those are all. That's an example of a quartic function. Okay, so let's do some examples here. Decide whether the function is a polynomial function. If so, write it in standard form, and then state the degree, type, and leading coefficient. So we got to remember what the definition of polynomial function was. Remember that was we had certain rules about the exponents and then about the coefficients. So we needed, can we just flip back to the rules here? Exponents are whole numbers, coefficients are real numbers. So for number 1 here, our exponents, that would be 2, that'd be 1, that'd be x to the 0. We have whole number exponents. The coefficients, we don't have any I, so I would say this is a polynomial function. So I'll write, whoops, let's spell it right, polynomial function. Okay, state the degree, type, and leading coefficient. Leading coefficient, I abbreviate LC. The degree, biggest exponent here is 2, and that's your answer for the degree. The type, think back to the table here, degree 2 is a quadratic function, so this is a quadratic, and the leading coefficient, that is the number in front of the biggest exponent. So the biggest exponent is actually here in the middle, it's not out front, so the biggest, or the coefficient on the biggest exponent here is negative 1.6. Now I forgot a step, so I did the degree, type, leading coefficient, I forgot to write it in standard form. So standard form would be f of x. Remember, standard form, the biggest exponent comes first, so that'd be negative 1.6x squared. Then the next exponent, or next exponent down would be minus 5x. And then the constant term, the one without the variable, is always left, positive 7. Okay, so f of x equals negative 1.6x squared minus 5x plus 7. Let's try another one here. Number 2, x plus 2x to the negative second plus 9.5. I would say this one is not going to be a polynomial function because we don't have the right exponents. This one is a negative exponent. Because we have this negative exponent, remember it violates that rule where exponents are whole numbers. Negative 2 is not a whole number. It's an integer, but it's not a whole number. So this is just not a polynomial function. And I abbreviate polynomial function with PF, okay, not a polynomial function. Number 3, q of x is equal to x to the third minus 6x plus 3x to the fourth. All of our exponents are real numbers, or whole numbers, positives, no negatives, no fractions. The coefficients, I don't see any I values there, so that means this is a polynomial function. Okay, so polynomial function. Let's go to degree, type, leading coefficient. Degree, type, leading coefficient. The degree, biggest exponent here is this one. It's a 4. A degree 4 function is a quartic function, Q-U-A-R-T-I-C, quartic function. Okay, the leading coefficient, the number in front of the biggest exponent, that would be a positive 3. So there's your statements about the function. Now let's write it in standard form. Let's see, our variable or letter this time is q of x. So q of x is equal to, we're going to have the biggest exponent first, 3x to the fourth. Then the next one down would be x to the third. And then the last one, minus 6x. That is in standard form for number 3. Number 4, h of x is equal to 0.5x squared plus square root of 3x cubed plus 19. Now, the square root of 3, this is a coefficient. It is not, the x is not underneath the square root, so maybe we'll add that little ender there so we can clearly see that the x is not underneath the square root. The exponents are all whole numbers. They're all positives. There's no negatives and no fractions, so we're good there. The coefficients, 0.5 is a real number. 19 is a real number. The square root of 3 is a real number. Okay, it's not. It's a number that we don't know. It's an irrational number, meaning it's a decimal that doesn't end or doesn't repeat. But that doesn't mean it's not real. It's a real number. So this one is a polynomial function. Okay, polynomial function. Okay, so then we can go to degree, type, leading coefficient. Degree, biggest exponent right there is a 3. If it's degree 3, that is a cubic function. And the leading coefficient is the number in front of that, square root of 3. Not a good number, but it's a number. Standard form, h of x is equal to, the biggest exponent comes first, so square root of 3 x cubed. Then the next one down would be x squared, so positive 0.5 x squared, and then positive 19. That is standard form for number 4. All right, what we can also do with functions is evaluate them. And evaluating simply means plug and chug. So we're going to take an x value that they give you, like in this one, x equals 3, and we're going to put that in for each and every x in our function. Okay, so, and there's also an x there. So f of 3 is equal to 2 times 3 to the 4th power minus 8 times 3 to the 2nd power plus 5 times 3 minus 7. Now, this you can all do in your calculator. 3 to the 4th power is 81, and then 81 times 2 is 162. 3 squared is 9. 9 times 8 is 72. 5 times 3 is 15 minus 7. This is f of 3 equals, and then this is all calculator work. When you type these 4 numbers into your calculator, you're going to find that f of 3 is equal to 98. That's all that means, is that the value when x is 3 is 98. So you can kind of think of it as 3 comma 98 is on the graph of f of x, if you were to graph that function. Okay, let's try another one here. G of x is equal to negative 3x cubed plus 2x squared plus x plus 6. Again, we're evaluating when x equals 3. So anytime we see an x, it's now going to be a 3. So negative 3 times 3 cubed plus 2 times 3 squared plus 3 plus 6. 3 cubed is 3 times 3 is 9 times 3 is 27. 27 times negative 3 is negative 81. 3 squared is 9. 9 times 2 is 18. Plus 3 plus 6 is 9. And then negative 81 plus 18 plus 9, this is g of 3, is negative 54. So this would be your answer for number 2. G of 3 is equal to negative 54. So if the directions say to evaluate, all you have to do, they will give you the x value. You need to just go ahead, put that in for every x, and come up with your number. Now, the biggest, or an important part of section 3.1 is the idea of end behavior. End behavior is the behavior of a graph as x approaches positive or negative infinity. And those are obviously big numbers. We can't ever write out that number. It's an idea that x is so large that we can't write it, or so small that we can't write it. End behavior falls into really 2 categories. Okay, every function, whether it's constant, maybe not so constant, but linear all the way up through degree 150 or 1,728 or any number you can come up with, every function basically has 2 different shapes, or every function could fall into one of 2 different shapes. Okay, so I'm going to focus first on the even degree functions. Okay, so even degree functions. End behavior is determined by 2 things. It's determined by degree, and then it's going to be determined by the leading coefficient. So LC positive, and then LC negative. Okay, so the degree and leading coefficient determine the general shape of every polynomial function. Okay, so if your degree is even and your leading coefficient is positive, your graph is going to have this general shape. Okay, this middle area, and I'm going to highlight that in red, this area in here is going to differ from every function. Okay, every function is going to look different in the middle. But what is important is that every function on the end is going to do the same thing. As x gets really, really big, way out here, this could be in the thousands or the millions, and this could be negative thousands or negative millions. As x gets really, really big or x gets really, really small, the function is going to do the same thing for each graph. Okay? Likewise, with the negative leading coefficient, your graph is going to have this general shape. And again, that part in the middle where it goes up and down, let me box that in. This part right here, that's going to be different for every function. But what I'm focused on is this business out here on the end. Okay? Every function that has an even degree, whether that's second degree or fourth degree or sixth degree or 100th degree or 1000th degree, every function has that general shape, specifically on the ends. Okay, so if the leading coefficient is positive, we could say this. Whoops, and let me go back to the pen here. As x goes to infinity, or as x gets really big, okay, and I'm going to replace big with infinity. Okay, so as x goes to infinity or gets really, really big, what happens to y? Well, as x gets really big, y is also going upwards. It's going to positive infinity on the y-axis. So as x goes to infinity, y goes to infinity. And then if we look on the other side, as x goes to negative infinity, as x gets really, really small, what happens to the y values? Again, they go upwards. So y goes to positive infinity again. Okay? That's the statement that we're going to be looking for, that you're going to be asked to provide when we're talking about end behavior. Okay? Now, for the negative side, if the leading coefficient is negative, and again, our degree is still even, we can say this: as x goes to positive infinity, as x gets really, really big, what happens to the y values? They go really, really small. They go to the negative y value. So y goes to negative infinity. And infinity is just kind of a sideways 8. It's kind of tough to draw. And then as x goes really small, as we go very far left on the graph, what happens to the y values? Again, they go downwards. Y goes to negative infinity. Okay? So there's the two statements for positive and negative leading coefficients on even degree functions, whether it's second degree or fourth degree or 10th degree or 100th degree or any even degree function. You're going to fall into one of these two categories, and it's all dependent then upon the leading coefficient, whether it's positive or negative. If it's positive, they both go upwards. If it's negative, they both go downwards. Now, what if the function is odd? So odd degree functions. Odd degree functions. Again, it's all determinant. If we have an odd degree, it depends on if the leading coefficient is positive or negative. If the leading coefficient is positive, your graph is going to look something like this. And again, this business in the middle, all of this, is going to be different from function to function. What's important, though, and what's going to stay the same is this general shape on the ends. Okay? Whoops, sorry, wrong button. Okay? If your leading coefficient is negative, your picture is going to look like this. And again, this business in the middle, going to be different from function to function, but the ends, as x gets really, really big or really, really small, they are going to have the same pattern. It's always going to look like one of those two functions, and it's going to depend on whether the leading coefficient is positive or if it is negative. So let's make our two statements here. So as x gets really big, what happens to y? Well, if we look at the graph, as x gets really big, y gets really big again. Whoops, not y goes to y goes to infinity, gets really big. And then as x gets really small, as x goes to negative infinity, what happens to y? So as x goes to the left, y goes down this time. Y goes to negative infinity. Okay, there's your two statements for the positive side. If we look at the negative side, so we could say as x goes to infinity, what happens to y? Well, as x gets really big, y goes downward this time. Okay, so y goes to negative infinity. And then as x gets really small, as x goes to negative infinity, that's a really bad negative, but we're going to go with it. What happens to y? Well, let's look. If we go really far left, y gets really big. Y goes to positive infinity. Okay, so even degree functions point the same direction, odd degree functions point opposite directions. That's how you can tell the difference between even or odd. Now the question then becomes, how do you determine if it's positive or negative? What I would tell you is look at the right-hand side of every graph. Look at the right end of every graph. Let me scroll that down. The positive functions on the right side, which way do they point? They both point upwards. The negative side, or the right-hand side, if they point downwards, those are both negative functions. Okay, so when it's asking you what type of function is this, all you need to do is look at the right-hand side of the graph. If it points downward, you can tell them that the leading coefficient is negative, and then if the ends point in the same direction, you can say that it's an even degree function, and if the ends point in opposite directions, you can say it's an odd degree function. Okay, so let's try a couple of examples here. Describe the end behavior of the function. So number one, the biggest exponent here is 3, so that makes it, so the degree is odd. The leading coefficient, that is I don't care what the number is, the LC is positive. Okay, so if the degree is odd and the leading coefficient is positive, we know that our picture looks something like this. No idea what it actually looks like exactly, but we know it's got that general shape. So then we can make our statements. So we can say as x goes to positive infinity, y is going to go to positive infinity again. So as we get really big on the x, we get really big on the y. And then we can say as x gets really small, what happens to y? Well, if you look, y gets really small again. So as x goes to infinity, y goes to infinity, and then as x goes to negative infinity, y also goes to negative infinity. That would be your answer, the one that I've boxed in here in green, that would be your answer for number 1. Number 2, let's try another one here, and keep those directions out of the way. The degree, biggest exponent here is 4. That is an even number, so the degree is even. The leading coefficient, and I'm just going to keep writing in red, negative 0.5. Don't care what the number is, I just need to know that it is negative. Okay, so if I sketch the graph, even and negative looks something like this. No idea if that's exactly the graph or not, I doubt it, but we're going to go with it. So then we can write our two statements. As x goes to infinity, as x gets really big, y goes really small, so y goes to negative infinity. And then as x goes to negative infinity, y goes to, so as x gets really small, y gets really small again. That would be your answer then for number 2. As x gets big, y gets small, and as x gets small, y gets small again. Last thing here in this section, graphing polynomial functions. This is pretty easy. You can use your technology to get the points, so you need a table of values. You get those from the calculator. Once you have your table of values, go ahead, plot your points, and then draw your curve. Okay? So let's go ahead and do number 1 here. So f of x is equal to negative x cubed plus x squared plus 3x minus 3. You can type this function directly into the calculator in the y equals screen. And then second graph will get you the table. And I'm going to put quite a few values in my table. I'm going to go negative 3, negative 2, negative 1, 0, 1, 2, and 3. Okay, I'm going to put 7 values in my table. I might not be able to graph all of them, but I can still have them on my table. So again, these numbers are coming exactly straight from my calculator. So 24, 3, negative 4, negative 3, 0. The x value of 2 gives me y of negative 1, and then 3 gives me negative 12. Okay, so there's my values. Let me bring in some graph paper here, and let's go ahead and sketch this. I'm not going to be able to graph negative 12, and that's okay. I'll graph what I can. So I got 0, negative 3 is here. Let's see, 1, 0 is there. 2, negative 1. 3, negative 12 is out. Negative 1, negative 4. And we're kind of infringing on the last example there, but that's okay. Negative 2, positive 3 is there. And obviously I'm not going to be able to graph 24 either. So I'm going to just basically play dot to dot and kind of draw my curve. And if you're not sure, go ahead and hit the graph button, and you should be able to see something that looks like that. I'm waiting for mine to come up as I speak. There was the first one, here comes the next one. Yeah, it looks something like that. If it does go above the x-axis, make sure you draw that in. It doesn't need to go terribly above. And this one, it barely looks like it crosses over, so it's not that huge of a deal if it doesn't. But your picture should look fairly close. I expect that since you can get these points from your calculator, you can plot them correctly and then at least play dot to dot like you're in kindergarten and preschool. That's the least that I think would be expected. Be able to put the points on the graph and then connect them with a curve. Let's try one more here. G of x is equal to x to the fourth minus x cubed minus 4x squared. Again, just put the points on or put the function in the calculator. Get the points from the calculator as well. Again, I'm going to do 7 points: -3, -2, -1, 0, 1, 2, and 3. And then these points from the calculator: 76. That's one I'm not going to be able to graph. 12 is out. 2. 4, 0, -4, and 22. Yeah, I'm not going to be able to graph 22. Probably won't be able to graph 12 either, but these 4 I think are realistic. We'll use the same graph. I'm out of space here. I can't scroll this thing up any farther, so we're going to have to kind of get cozy with our picture. We'll do this in red. So 0, 4 is there. 1, 0. 2, -4 is down there. -1, +2 is there. And those are the points we'll be able to graph. If you're not sure, go ahead and check your calculator, and your graph should look something like this. So what you notice, I did not just drop this off at the end, because if you look, 322 is way back up this way. Okay, so I need to make sure that my graph matches, so you can use your calculator to check yourself and to kind of give you a guide of what this graph is supposed to look like. So that's kind of an overview of section 3.1. Hopefully all of that made sense. If there's something that you're confused about, please make sure you jot down any questions and then ask me in class.